and welcome, strange people of the internet. I am Kiara Blows. I am a current biomedical sciences. Sorry, my dog just ate something. Life of being a dog owner. I am a biomedical sciences student at Newcastle University, and I'm going to be your physical sciences tutor with Tutorbox Live in conjunction with COVID-19 catch-up courses. So I hope you are as excited as I am to get our think on. You know, this lockdown is just, you need to engage your mind. Right, we know that. So I know a lot of people are very intimidated by physical sciences, and it is said to be the most difficult subject, maybe. And it definitely does have its difficulties, but I think you just have to know what to look out for, tips and tricks, which I will definitely share with you. And who knows, maybe you'll get the marks you've always wanted, which I believe in you 100%. And so I just wanted to I'm so proud of you for taking the time out of your day to sit here and listen to what I have to say, because I'm not a very interesting person, but I can help you with science, so we'll go with that. And yeah, so grab your notebook, probably your worksheet that you were sent with us, some writing materials, your willpower and your brain, and perhaps a very caffeinated beverage, and let's get started. So welcome. Our first lesson is going to be on transverse pulses. Woo! So I hope you are all ready to get started and smash this lesson, because it's exciting stuff today. So we're going to start off with our introduction and definitions. I know this can be a little tedious, I know, but trust me, towards the end of your physical sciences, you'll thank me for going through definitions, because they're the easiest places to get marks in your exam. Okay, so a medium is the substance or material the pulse moves in. So this can be air, this can be water, any type of liquid, solid, or gas. The pulse is a single disturbance that moves through a medium. So if you imagine all the little particles, the pulse disturbs those particles. So me speaking right now is disturbing the air particles around me. If you jump in the pool after this lesson because your brain is on fire, then you're disturbing that water medium. Okay, so the pulses we're going to be focusing on today are called transverse pulses. So this is a pulse where all of the particles disturbed by the pulse move perpendicular to the direction of the pulse. So if the pulse is, for example, moving straight ahead, the particles will be moving left or right. The amplitude of a pulse is the maximum disturbance, or the distance the medium is displaced from its rest position, and is measured in meters, which makes sense. It's the maximum disturbance, so it's the maximum the medium will be displaced and moved, so it's a distance. Pulse speed is the distance a pulse travels per unit time, and that is meters per second. So in this diagram, we've got the position of rest, also called your equilibrium position, and these are interchangeable. And then we've got our disturbance occurring here, our amplitude, and then we've got how long the pulse lasts, and then our pulse speed will be the distance per unit time. Okay. Technical difficulties here. Right. Next, we're going to talk about superposition of pulses. Okay, so two or more pulses can pass through the same medium at the same time in the same place. So, for example, a single disturbance would be you jumping in the pool after this lesson, whereas two or more pulses at the same time would be if you and your sibling or your friend jumped in at the same time. Hopefully not your friend, you're supposed to be social distancing. Okay, and then when they do interact with each other, they form a different disturbance. So how they interact with each other will determine the output. So the principle of superposition states that when two disturbances occupy the same space at the same time, the resulting disturbance is the sum. Okay. After the pulses pass through each other, each pulse continues along its original direction, and their original amplitudes remain unchanged. So constructive interference is when two pulses meet, resulting in a bigger pulse. So this is if you and your friend were to jump in the pool at the exact same time, you make a much larger splash. Destructive interference is when two pulses meet, resulting in a smaller pulse. So this is when the two somehow are exactly the same in amplitude, but in opposite directions, or inverted and stuff like that, and they cancel each other out. Okay, so these figures just show the constructive and deconstructive, or destructive rather. So pulses move towards each other, and then one thing is this, remember, it's the sum. So if you've got two positives, you'll get a double mass as such. And then at the end, they're exactly the same. So this can be either in that direction or that direction. As long as they're both the same, they're considered then positive, if you will. However, these two are exactly the same, but they are in opposite directions. And then when they destructively interfere, they'll cancel each other out. This is more so done in like sound waves, where if two sound waves interact with each other, instead of having a big sound, you have no sound. Okay, it's not really something you will probably encounter in your daily life. Constructive interference is a lot more common. Okay, so like it says, it can either be that way, they were exactly the same, or one can be slightly bigger, and then the slightly bigger one will just, the interference at the sum will then just be a little smaller. So it's like decreased. Alright guys, so that has been our first little section. I'm going to go over one example with you very briefly, and then there will be a few others for you to attempt, and hopefully they go okay. And then I shall post a bit of the answers. So it says a pulse covers a distance of 5 meters in 15 seconds. Calculate the speed of the pulse. So we write out velocity is equal to distance over time, which is equal to 5 divided by 15, which is equal to 0.33 meters per second. Okay. Remember that the pulse speed depends on the properties of the medium and not on the amplitude or the pulse length. Alrighty, so now I want you to attempt questions 2, 3, 4, 7, 8, and 9. And try your best, and good luck. It's me again. I'm just getting sick on my face. Alright, so we're going to go through the questions to part 1. Hopefully you've done all of them, attempted all of them. They were okay. It's very basic, but we'll go through them anyway. So our first one was that pulse has a speed of 5 centimeters per second. How far does it travel in 2.5 seconds? So we want distance. We're going to say distance is equal to velocity times time, or speed rather than velocity, which is equal to 2.5 times 5. Note, if you're timesing centimeters per second by second, your seconds will cancel out and you will get centimeters. So in this case, it doesn't matter. You don't have to change your speed or anything. Okay, and then the third one, a pulse has a speed of 0.5 meters per second. How long does it take to cover a distance of 25 centimeters? So this is a case where you do have to change it out. So we're going to say our time is equal to distance over speed. So we've got 25 centimeters or 0.25 meters over 0.5 meters per second. And your meters cancel out and you get 0.5 of a second. Okay, last one. How long will it take a pulse moving at 0.25 meters per second to travel a distance of 20 meters? So we want time here. So we've got time is equal to distance over speed, which is equal to 20 meters over 0.25 meters per second, and you get 80 seconds. You can convert that to like a minute 20 seconds if you want to, or you can just leave it as it is. And then our other two questions were, or the three. What is superposition of waves? So we're just going to put the principle of superposition in here again. States that when two disturbances occupy the same space at the same time, the resulting disturbance is the sum of the two disturbances. So then just for the principle of waves, you would just replace disturbance with waves. Okay, hopefully that is straightforward enough. And then we're going to say, what is constructive interference? So constructive interference is when two pulses meet, resulting in a bigger pulse, right? So you add them together and it is positive. And then what is destructive interference? So that is when two pulses meet, resulting in a smaller pulse, or no pulse at all basically, but you can just say smaller pulse. And that is part 1 finished and complete. And I'll see you for part 2. Welcome to part 2, and I know what you're thinking. This is just too much, my brain is exploding, but we're almost there. We just have part 2 left. So we're going to deal with transverse waves. So firstly, what is a wave? It's a periodic continuous disturbance that consists of a train of pulses. A transverse wave, can't speak English. A transverse wave is a wave where the movement of the particles of the medium is perpendicular at a right angle to the direction of propagation of the wave. Tongue twisters, I tell you. This diagram just shows you the particle motion and the wave motion. So remember, a transverse wave moves perpendicular to the direction of the particles. Okay. When the particles of a medium move at right angles to the direction of propagation, it's called transverse. For waves, there is no net displacement of the particles of the medium because they return to the equilibrium, but there is a net displacement of the wave. There are thus two different motions, the motion of the particles of the medium and the motion of the wave.
Ever seen a Mexican wave at a sporting event? The effect is a pretty cool display that goes all around the stadium, but no one has had to move seats. All waves can transfer energy from one place to another without transferring any matter. This is done by a series of disturbances or vibrations that carry the energy. Just like the people in their seats only moving up and down when it's their turn. Waves can transfer energy through solids, liquids, gases and empty spaces, otherwise known as vacuums. There are two types of waves, which we look at in more detail in another video, but the basic features are the same. These four words describe different properties of waves. Let's discover what each one means. The frequency of a wave is the number of complete waves passing a fixed point in a given amount of time. This time period is usually 1 second. This is what one complete wave looks like. So if this was our time period, the frequency would be 5. Frequency is given the symbol F and is measured in units called hertz. Hertz measure how many complete cycles per second. So how many people in our Mexican wave stand up every second. The frequency and period are often confused. The frequency refers to how often something happens, whereas the period refers to the time it takes to happen. The period of a wave is the time for one complete cycle, so the time taken for one person to stand up, wave, and sit down. This would be measured in seconds. When something happens repeatedly, we say that the event is periodic, and refer to the time for the event to repeat itself. The period of the Earth to orbit the Sun is 365 days. The period of a day is 24 hours. The period of a typical class at school is 45 minutes. Now for wavelength. The wavelength is the distance between a point on one wave and the same point on the next wave. For example, two peaks or two troughs. Wavelength is given the symbol lambda from the Greek letter and is usually measured in meters. Wavelength can vary hugely in size. X-rays are very short, visible light is here, and FM radio waves are much longer. So we've looked at the frequency, period and wavelength so far. Let's finish with amplitude. As waves travel, they create disturbance. The amplitude of a wave is the distance from the maximum disturbance to the undisturbed position. Think of a very flat sea, and then an incoming wave. The amplitude is the height of the top of the wave from the flat sea. Can you add the labels to these waves and work out the frequency? Notice that the top one is distance and the bottom one is time. Pause the video, work it out and click play when you're ready. Did you get them right?
Okay. Properties of waves. So this is a very simple diagram of a wave, and we've got the equilibrium as the dotted line. So your crests are what are shown at the top and your troughs are what are shown at the bottom. So just for more definitions, a crest is a point on the wave where the displacement of the medium is at a maximum. So that just means from the equilibrium, that's the max that it'll go up to. So that's showing like your positive direction. And then a point on the wave, if the displacement of the medium is at a minimum, will be your trough. Okay. So what is your wavelength? That's denotated by this weird looking symbol, but you know, the Greeks were weird, and it is called lambda. So what is a wavelength? So it's the distance between any two adjacent points. So you can go from the top of a crest to the top of another crest, from the top of the trough to the top of the other trough. You could go from that little point there to that little point there. They'll all be exactly the same as long as the waves are in phase. And the wavelength is obviously a length, so it's measured in meters. You can see that this is an amplitude, but so is this, it's just in the negative. So this will technically be 2 times your amplitude. and we've already covered this, but just to reiterate, the amplitude of a wave is the maximum disturbance or displacement of the medium from the rest position. Okay, so we're going to just quickly try and attempt a few exercises from exercise 8.1. Okay, so we're at the final stretch. I am just going to bring up the questions and briefly talk over them and just show you the answers so you know you're on track. Okay, so our first one says when the particles of a medium move perpendicular to the direction of the wave motion, the wave is called a, hopefully so transverse, because that's all we've been talking about today. Okay, the second one says a transverse wave is moving downwards. In what direction do the particles in the medium move? Just remember perpendicularly, because if it's moving downwards, your perpendicular will be left and right, so you can say both, or you can just say perpendicular because it won't just be right and it won't just be left. 3. Considering the diagram below, answer the questions that follow. So we've got a wavelength of the wave is shown by letter. So remember wavelength is point to point. So what is A? It is 2 times the amplitude. C is technically from crest to trough, so that's only half a wavelength. And B is 1 amplitude. So that means it's D, going from the same point on one wave to the same point on the other. Okay, next step. A heavy rope is flicked upwards, creating a single pulse in the rope. Make a drawing of the rope and indicate the following: the direction of the motion of the pulse, the amplitude, the pulse length, and the position at rest. Okay, so this is very similar to what the drawing is in question 3. So hopefully you just drew it and you indicated your amplitude, similar to how you would in 3B. The pulse length, remember, what would that be? So that would also be similar to your wavelength. Your position at rest, so that would be a dotted line or a straight line. Okay. Second one, a pulse has a speed of 2.5 meters per second. How far will it have traveled in 6 seconds? So we use our formula, velocity is equal to distance over time. We rearrange that so we get distance is equal to velocity times time. So we take 2.5 multiplied by 6, and that gives you 15 meters. Okay. 3. A pulse covers a distance of 75 centimeters, 2.5 seconds. What is the speed of the pulse? Okay, so hopefully you noticed that it was centimeters and you have to convert it to meters. A little tip is just remember millimeters to centimeters, you divide by 10, centimeters to meters, you divide by 100, and meters to kilometers, you divide by 1,000. And then obviously if you're going from like millimeters to meters, you just add all of those. And then if you're going the opposite direction, you just multiply. Little tip that always helped me, so hopefully it'll help you. So that means that we have converted our centimeters to meters, so we have to divide that by 100. And we got the speed, so we take 0.75 divided by 2.5, and you should get 1.9 meters per second as your answer. Notice it said speed. Remember, speed is scalar, so it doesn't need a direction. Velocity would need a direction. And in this case, actually, you should write speed is equal to instead of velocity is equal to. How long does it take a pulse to cover a distance of 200 millimeters if its speed is 4? So remember millimeters. So we're going to go millimeters to centimeters to meters. So we have to say 200 divided by 10, and then that answer divided by 100, or technically 200 divided by 1,000, which is 0.2 meters. And then I want time. So you've got your speed is equal to distance over time. So your time is equal to your distance divided by your speed. So say 0.2 divided by 4, and you get 0.05 seconds. Okay, so I hope that was all pretty clear and you understood all of it.
In this simulation, I want to briefly discuss a transverse wave and some of the things that you can measure by observing a transverse wave. The first thing you need to recognize is that a transverse wave is generated by a vibration. And in this case, the vibration is this pole that's traveling up and down. You'll note that the vibration of the particle is actually perpendicular to the direction of the wave that's going out the window. And each particle is doing exactly the same thing. They're simply vibrating vertically, in this case, to the direction of the wave, which is horizontal. And if you look at each of the green dots, and I can slow it down for you to make it a little bit easier, you can clearly see that each particle is simply vibrating perpendicular to the direction of the wave. Now, if I pause the wave, you'll notice a couple of things. First of all, there is an amplitude. The amplitude is simply the maximum height that the wave has. In this case, it's measured from the top of the crest to the equilibrium line. Of course, the amplitude can also be measured from the equilibrium line down to the bottom of the trough. But as long as there's no energy loss, the amplitude remains the same throughout the motion. The next thing you can measure is the actual distance. You'll notice that the cycle, in this case, the cycle is represented by this sine curve, is that the distance from crest to crest repeats, and we call this distance the wavelength. Of course, I can measure the wavelength also from trough to trough. Or in fact, I can measure the wavelength from any two particles that are actually totally in sync with each other. So for example, this dot here and this dot here, if you were to observe it, and I may need to slow it down, you'll see that they're generally speaking, they're going to be in sync with each other. Now, it's not very clear here, but nonetheless, two particles that are in sync with each other, they are separated by one wavelength. Now what happens, what else can be measured here? Well, clearly there's a rate at which this piston vibrates, and there's two aspects that I can measure. I can either measure how long it takes to complete one cycle or one loop or one vibration, and that's called the period. But the other way I can measure it is by referring it to the frequency. And the frequency is the rate at which this actually vibrates. So if I increase the frequency like this, you can clearly see that the vibration increases. In this case, it's going at roughly 2 Hertz, or 2 times per second. Therefore, the time can also be determined in terms of its period. In other words, it takes 1/2 of a second for it to go one complete cycle. And the period and frequency are basically reciprocals of each other. What else did you notice as I increase the frequency and decrease the frequency? Well, clearly the wavelength changes as well. The wavelength increases if I decrease the frequency. And as I increase the frequency, clearly the wavelength decreases. What that means is that they are inversely proportional to one another. As one increases, the other decreases. But have you noticed something that doesn't change? That's right, the speed. The speed remains constant. Whether I increase the frequency or decrease the frequency, the rate at which the wave moves out through the window clearly remains the same. And that's because the product of the frequency and the wavelength equals the velocity of the wave. V equals F lambda, and that's often referred to as the wave equation, and one of the most important formulas in the understanding of waves. So the speed remains constant. If you increase the frequency, you decrease the wavelength. So if I speak in a high voice, the wavelength has decreased. If I speak in a low voice, the wavelength has increased, but the speed remains the same. If I change the amplitude, of course the peak gets smaller, but neither the frequency, nor the wavelength, nor the speed changes. So how can I change the speed of a wave? Well, the only way to change the speed of a wave is altering the medium or the material that the wave passes through. So in terms of air, my voice is traveling currently roughly around 330 meters per second. But it varies with temperature because temperature changes the density of the air. So similarly in this string, if I change the tension of the string, then I'm changing the medium. And so I can lower the tension, and you can clearly see that the speed of it decreases. Increasing the tension, the speed of the wave increases. And so this shows as well that the medium can alter the speed of the wave. But notice that the wavelength and frequency do not change when I change the tension. I hope that gives you a bit of a better understanding of how transverse wave works.
Alright, so that has been your first lesson complete. I hope all the information, examples, and concepts were helpful. I know it was a lot of definition and very definition heavy, but I hope you go away and just feel a bit more confident understanding the concepts and that you're engaged as much as possible. That's all we can ask of you. So just a reminder, I am Kara Blows and I was your physical sciences tutor. And this has been Tutorbox Live in conjunction with COVID-19. There will be a Q&A session, and I think there is another session after this. So please tune in again soon. It was lovely to meet all of you, and I hope to be teaching you all again soon. Enjoy your day, stay safe, stay hydrated, and stay active. Bye.
It's not a matter of whether or not we can. Everybody can, but not everybody will. How to turn nothing into something. How tangible are ideas and imagination? Ideas that become so powerful in your mind and your consciousness, they seem real to you even before they become tangible. Imagination that is so strong that you can actually see it. You can actually see it. If somebody cannot see it when it is not here, then it will never be here. Start looking into the future of what you would like to accomplish, where you would like to go, the person you would like to be. Decide what you want, and then act as if you already had it. And that is to believe that what you imagine is possible for you. So the first step is to imagine what's possible. Second step, to believe. Now here's the third step, and that is to go to work and make it real. You now go to work and make it a movement. You make it tangible. You make it viable. You breathe life into it, and then you construct it.
You have a lot to offer. The fact that you're still here means that your business is not through yet. People don't do what they know in life, but what they do is they operate within the context of the vision they have of themselves.
So write and draw and build and play and dance and live as only you can. Make up your own rules. The rules on what is possible and impossible were made by people who had not tested the bounds of the possible by going beyond them.
You must change what's possible for you. You, and only you, are the subject that impacts the burning desire in your imagination. You are living and feeling as if your future dreams are a present fact.
Will it be easy? No. Will it be challenging? Yes.
So you got to prepare yourself. You've got to develop yourself. Long as you're breathing, you got some more work to do. There's something else for you to achieve. Guess what? You're going to make some mistakes. You're going to make a lot of mistakes.
So now go and make interesting mistakes, make amazing mistakes, make glorious and fantastic mistakes. Break rules, leave the world more interesting for your being here. Make good art.
It is possible to start with nothing and become something.